So we're talking about constant velocity motion and a quick video on equations for a constant velocity motion, especially when we're looking at a position time graph. So if we imagine this y-axis to be position and this x-axis to be time, here we see a beautiful straight line. And our friend Desmos here shows us that that equation is y equals mx plus b. We've seen that a lot in this first part of the year. If we make the slope steeper, if we make the slope a larger number, our graph is steeper. That means we have a greater velocity. If we make our slope going the other there, if we make our slope go in the other direction, then we have a negative slope, and that just means that the object has a constant velocity but is going in the negative direction. Regardless, the general form for the equation is y equals mx plus b. We would simply change that to d equals vt plus do, and we've done that a fair bit. So for any position time graph, if the velocity is constant, then the equation for the position time graph would have to be some sort of a linear relationship. Y equals mx plus b. When we convert that to positions and times, the position is some number times time plus our y-intercept. An example of something that is not a constant velocity relationship. I did a little bit of moving around, so we'll take a look at it. So we just looked at this graph for a constant line that has this y equals mx plus b relationship, which can be then converted to position is velocity times our time interval plus the starting position. Then if we look at examples for graphs and equations that are not constant velocity for a position time graph, if we have a position time graph that's got a delightful curve like this, ooh, beautiful. So this position versus time graph, this is not straight line, there's a curve to it. We have y equals ax cubed for this graph. And if I change y to what's on our y-axis, that's position. I change x to what's on our x-axis, that's time. So we have we have position equals some number times time cubed. That gives us this pretty little curve. So then the question becomes, is this graph and this equation a representative of constant velocity? Well, if we're looking at the equation, or pardon me, if we're looking at the graph, well, there's a curve to it. And if there's a curve, then our slope is changing. And if our slope is changing, then our velocity is changing. If we look at our equation, we don't have a y equals mx plus b format, where here we have position, velocity, time. We have position with no exponents, no squareds, no cubes. We have time with no exponents, no squareds, no cubes. So when we go down here, if we see that time is squared or time is cubed, that's an indication that our velocity is not constant. That's an indication that the velocity must be changing. So is this constant velocity? Heck to the no. That's it for this part.